All right, today we're going to talk about graphing polar equations and then finding the area that the area of the region that's enclosed by a polar graph. So the first thing I want to do is I'm going to actually derive the formula that you're going to use. The formula for the area of a polar region is 1/2 integral from a to b of r squared d theta. And the reason that this is the formula is that most polar graphs have some sort of curvature to them, and they're kind of circular in a sense. So if I wanted to say find, if this is some polar graph right here, and I want to find the area that's in that first quadrant right here, what I'm going to think of it as is I'm going to think of it as finding the area of sectors of a circle. Now, it may not be, this curve may not follow a perfect circle right here, but I can at least estimate that area by using sectors of a circle. Just kind of like in normal in function mode when we estimated the area using rectangles. The rectangles wouldn't exactly fit underneath that curve, but we could at least use it. All right, so let's think back to geometry and how to find the area of a sector. The area of a sector, let's let be A. And the formula for finding that is the area of a sector over pi r squared equals an angle measure over 360 degrees. It's basically just a proportion. The area of that sector is a portion of the full circle, and the formula for a full circle is pi r squared. And that sector is basically cut off by an angle measure, and that angle measure is part of the full 360 degree circle. So if I solve that formula for the area of the circle, I would multiply both sides by pi r squared. So theta over 360 times pi r squared. But in calculus, we think about everything in terms of radians. So 360 degrees is the same thing as how many radians? 2 pi. So theta over 2 pi, and then times that pi r squared. So the pi's will cancel, and I'm left with 1/2 r squared theta. And you probably never thought of it in terms of that. You'd probably just, in geometry, solve this proportion right here. But this is just another way to think of the area of a sector. So if you have the angle measure that that sector is encompassing, like a 30-degree angle measure, or in terms of radians, pi over 6, and then the radius of that sector, then you could find the area of that sector. Well, if I wanted to find the exact area of this whole section in the first quadrant, then what I would want would be for the number of sectors to approach infinity, and then theta to approach what? 0, which is essentially an infinite Riemann sum, and I can get that by doing what? Integrating, right. So essentially that theta, which we want to approach 0 and have an infinite number of rectangles, becomes my d theta when I integrate. So the formula is 1/2 the integral of r squared d theta. And then you would integrate between whichever two angle measures you're talking about. Like in this case, I was talking about the first quadrant, so I would integrate from 0 to pi over 2. So that's where that formula comes from. No, you will not have to come up with that formula. I mean, you'll have to know the formula to use, but you won't have to derive the formula on a quiz or test. Right? That was just kind of to help you understand it and to help you visualize it. So when we're talking about finding area of any of these regions, you need to think of it more in terms of sectors as opposed to rectangles. So you've got to get out of that rectangle frame of mode that we used in function mode. Frame of mind, I'm sorry. All right, so write an integral that represents the area of the shaded region of the graph of r equals 1 minus sine theta. The easy part is just plugging the stuff in for the formula. So it's obviously going to be 1/2 integral. You're given the r equation, so r is 1 minus sine theta. The formula says to square it. And then the only thing that you really have to think about are the limits of integration. So between which two theta values do you need to integrate that? Well, the easiest way to think about this is when you're looking at this graph right here, this is where theta is 0. What's the angle measure up here on the positive y-axis? Good, pi over 2. And then over here, the angle measure is pi first, and then 3 pi over 2. Okay, and when you graph a polar equation, or when the calculator graphs a polar equation, it's going to start by plugging in 0 for theta, and then continuing with basically like pi over 6, pi over 3, pi over 2, and all of the numbers in between. So if this is where, so I basically want to look on the graph where theta is 0. So if the calculator were to graph this, it's going to start right here and then continue towards pi over 2, and then continue towards pi, and then all the way around like that. So what theta values encompass that shaded region, do you think? Pi over 2 to 3 pi over 2. Good. And it just says write the integral that represents that. A lot of times it will actually say find the actual area, and then we'll use our calculator to type that integral into the calculator and find the value of that area. Okay, number 2 is write an integral that represents the area of the unshaded region. Now, what can you probably tell me about that shaded region and the unshaded region? They're equal to each other, right? So if it said, if the directions say just find the area of it, you could just, if we found the area in part 1, then we could just say, oh, well, it's the same thing in part 2. But if I want to write an integral that represents the area of that unshaded region, I need to get my limits of integration correct that represent that unshaded region. So does anybody have any suggestions on what limits to use? Okay. I could use negative pi over 2 to positive pi over 2. And everything else is going to be exactly the same. Can I put 3 pi over 2 on the bottom and pi over 2 on the top? And would that be an accurate representation of that area? Right, it would make that area negative because my bottom number is bigger than my top number. So I can't just use 3 pi over 2 to pi over 2. What if I was just insistent on using 3 pi over 2? What if I wanted to use positive 3 pi over 2 down here on the bottom? What would the top limit have to be? 5 pi over 2. There you go. Yeah, and basically I just need to continue on. If this is 3 pi over 2, then technically when I trace around here, this is 2 pi, and then I'm going another pi over 2 to get back there. You can just continue to trace out that graph forever and ever and ever. But so it doesn't matter. Either one of those would be acceptable. And I could see them asking like a multiple choice question like that of write an integral that represents the area of either a shaded region or an unshaded region, and then giving you different choices. Now, they would never give you both of those choices because both of those choices are correct.
It's always just like counterclockwise.
Yeah, and it's basically you're just going counterclockwise from a starting point, and you don't ever want to go backwards. It's a good way to look at it. Write an integral that represents the area of the shaded region of the graph of r equals 1 minus cosine 2 theta. If you just kind of visualize tracing this graph, when I hit this point right here, what is the likely theta value of that point? Pi over 2, right? So if I want to go all the way around that shaded region, what do you think the limits of integration are going to be? Yep, 0 to pi, because pi over 2 is kind of smack dab in the middle of that. Then 1/2 integral 0 to pi of r squared. All right, let me show you on your calculator how you can kind of use the calculator to trace the graph in case you're just a little bit iffy on the theta values. So if you graph this, which is 1 minus cosine 2 theta, remember that you have to use theta. And for your window, you always want to go, your theta min and max needs to be between 0 and 2 pi. And that theta step is pi over 24. And if you use pi divided by a number, then when you trace, you'll know like when you hit exactly pi and pi over 2 and things like that, because you'll recognize those numbers. And then in terms of the x min and max and the y min and max, you may just kind of have to play with that. All right, so I'm actually going to zoom in since that's so small. And if you actually watched it while it traced out, it started at theta equals 0 and then went around. And so it started right here and then went around like that. But we can trace by doing F3. And we can see that it started at, see where it started at theta equals 0. And then when I trace it all the way around that top circle, you can see that when you get back to the bottom of it, it's down at pi. So from 0 to pi. But most of the time it's fairly intuitive, or at least you'll see those angle measures with practice. All right, let's find the area that's enclosed by the graph of r equals 5 cosine 3 theta. Up until, or so far on the AP exam, they've always either given you a picture or let you use your calculator to graph it. So I'm hoping that that will be the case, that they will always either give you the picture or let you use your calculator to graph it. So since I have no idea what that graph actually looks like, I need to use my calculator. And that's kind of big, so I'm going to zoom out. You may have to draw the graph on a quiz or a test, but I would let you use your calculator to do that. All right, so I want to find the area that's completely enclosed by this. The wonderful thing about polar graphs is that they are very symmetrical. You can pretty much assume, if it just even halfway looks symmetrical, you can assume that it's symmetrical. So all three of the petals of this flower are the exact same area. So what we could do is we could just find the area of one of those petals and then multiply it times 3. For that matter, I could even find the area of the top half of one petal and multiply it times 6. And the reason that this top half of this petal is a good choice is because when you trace this graph, or when you start with theta equals 0, this is where theta equals 0, right over here. So the way that this graph is traced out is it comes around like this, and then I think it came down like that, but it goes this direction. You don't want to just integrate from 0 to 2 pi because it's going through the pole and then coming back towards the pole. It's kind of going back over each other, and so it'll kind of erase some of that area if you just integrate from 0 to 2 pi. So you basically just want to take one little section of it and then multiply it by whatever the symmetry is. So I'm going to integrate from 0 till whenever this graph hits the pole right here. So how can I figure out at what theta value this graph hits the pole right here? You can't use intersect on your calculator because all the F5 features are grayed out. And in fact, I want you to think about a way algebraically that what's significant about the pole? Right. It's the point 0, 0, or it's the point 0, comma, any angle. It could be any angle, but the radius is 0 at that point. So the graph will hit the pole when r equals 0. And I have an equation that's in the form of r equals, so if I set the equation equal to 0 and solve that equation, I can figure out when the graph hits the pole. So if I divide both sides by 5, I get the cosine of 3 theta equals 0. What angle has a cosine of 0? Pi over 2 and 3 pi over 2.